Welcome to chapter 5.4, the hypergeometric probability distribution. In this section, we'll explore a distribution that applies to situations where the trials are not independent, specifically when we're sampling without replacement. You'll see this used in quality control testing, surveys, card games, and real-world audits. We'll learn how to compute hypergeometric probabilities, calculate the mean and variance, and understand how this distribution differs from the binomial. The hypergeometric distribution is used when we are drawing a sample from a finite population without replacement, meaning once we select an item, it does not go back into the population. This changes the probability on each draw, making the trials dependent. Let's say you have a deck of cards and you're drawing 5 cards without replacement. The probability of getting a heart changes with each draw since you're removing cards as you go. This distribution tells us the probability of getting exactly case successes in trials drawn from a population of n items, capital N items, where capital M of them are successes. Here's the formula that defines the hypergeometric probability. It's going to be capital M choose K times capital N minus capital M choose lowercase n minus k, all divided by capital N choose lowercase n. Each component of the formula reflects a part of the sampling process. Capital M choose K is the ways to choose the case successes. Capital N minus capital M choose a lowercase n minus k is the weight to choose the remaining failures. And then capital N choose lowercase n is the total number of ways to draw a sample of lowercase n from capital M. Each of these are calculated using this formula. Just plug in the values. You'll usually use technology like a calculator or Excel to compute these quickly. The hypergeometric distribution is appropriate in situations like drawing items without replacement, populations that are small and known, situations where probabilities change between draws. So some real-world examples of these include selecting light bulbs from a batch of 100 to test for defectives, choosing students from a dorm for a survey, drawing cards from a deck where each draw alters the makeup of the deck. Or a classroom example. Suppose you're picking 5 students at random from a room of 30 and 10 of them got A's on the last exam. What's the chance that 3 of your picks are the A students? Here's a practical example. A case of 12 wine bottles contains 3 that are spoiled. A student randomly selects 4 bottles to serve at a dinner. What's the probability that exactly 2 of them are spoiled? So this is a hypergeometric situation. Capital N would be the 12 total bottles. Capital M would be the 3 spoiled bottles. Lowercase n is the 4 that we select. And k equals 2 are the 2 spoiled ones we're looking for. So we'll plug these into the formula and compute the probability. All right, so plugging in looks like this. Using that formula, we're going to get, just doing each of those separately by hand with our calculator, about 0.21. Now, we can get this a lot faster. We can go to Excel. We can go to Excel. Go. So this time we're doing hypergeometric. There we go. So I want that. HGEOM distribution. Okay, so our sample, K is 2. The number, N is 4. Our population, M is 3. And the number total in the population is 12. We do not want it to be cumulative, so we're going to put false. And there we get the 0.218, the same thing that we found doing it by hand. All right, so there's about a 21.8% chance that 2 of the 4 bottles are spoiled. Hypergeometric problems often involve these kind of combinations, and technology is very helpful for calculating them efficiently. Just like other distributions, we can calculate the mean and variance of a hypergeometric distribution. Our mean is lowercase n times capital M divided by capital N, and the variance would be sigma squared is equal to little n times capital M over capital N. Now notice that that's just the mean, right? So I can put the mean there. And then multiply by capital N minus M divided by capital N times capital N minus N divided by capital N minus 1. Notice that the variance includes an adjustment factor. This guy right here. That's the finite population correction. It adjusts for the fact that each draw changes the population. Imagine you're selecting 10 students at random from a dorm of 40. Out of those 40, 10 attended a campus event last weekend. What's the probability that exactly 4 of the 10 selected students went to the event? This is a hypergeometric problem because we're sampling without replacement from a known population. Capital N is the 40 in the dorm. Capital M is the 10 event attendees. Lowercase n is the 10 students selected. And K is the 4 event attendees in a sample. This mirrors many real-world survey or quality check settings. We plug into the formula again. Rather than computing each term by hand, right, we'd go to Excel or a calculator. In this case, we're going to do Excel. So, okay, so again, we're doing hype. Okay, so here our K is 4. Little n is 10, capital N is 10, and then big N is 40, and we are not doing cumulative, so again, we're going to do false. 0.147, which is exactly what we found on the slide here. So there's about a 15% chance that 4 of the selected students went to the event. This kind of probability model is useful in predicting responses and planning sampling strategy. Let's take a marble spin. So Shield has 15 recruits and 6 of them are already trained field agents. Nick Fury selects 5 recruits at random for a stealth mission. What's the probability that exactly 3 of them are trained? Again, we're not replacing recruits once they're picked, so this is hypergeometric. Capital N would be my 15 recruits. Capital M would be the 6 already trained agents. Lowercase n would be the 5 that we're selecting for the stealth mission. And k equals 3 is how many we want that are already trained. So we would compute by plugging into our formula. And then we're just going to go to Excel and type it in again. So again, we'd do that hypergeometric distribution, would do 3, 5, 6, 15, false, because we're not doing cumulative. And you should get about 0.23976. This helps shield balance stealth with training. So to summarize, use the hypergeometric distribution when sampling without replacement from a finite population. It's great for real-world scenarios like quality control, card games, and audits. The probability of success changes on each draw. That's what distinguishes it from binomial. Use the formula or technology to compute probabilities, and don't forget the finite population correction and variance. If you're drawing a hand of cards, surveying a small class, or running covert missions at SHIELD, the hypergeometric model gives you the precision to predict outcomes.